In question 4.1 we're asked to state Lenz's law. Well, this is that the direction of an induced EMF is such as to try to oppose the change of flux producing it. In 4.2 we have a diagram where to state how the reading on the ammeter will change during the process shown in the diagram. Well, the ammeter will show a current flows as the magnet moves, going back to zero when the magnet stops. In 4.3 we're to explain how this demonstrates Lenz's law. Well, the magnet will increase the flux to the left through the coil. The current E to F produces a flux to the right. This will produce a north pole on the right hand side of the coil. This gives a repulsive force on the approaching magnet. In 4.4 we have a diagram of a square coil moving into a magnetic field, where to calculate the time taken to move the coil from G to H. Well, for this we can use that EMF is equal to magnetic flux density B times the length L times the speed V, and V is S over T, so you can write EMF is equal to BLS over T, or T is equal to BLS over the EMF E. Magnetic flux density is 0.38 Tesla. The length is 32 millimeters. The distance it has to travel is 32 millimeters, so I can just square this term. And the EMF we get is 2.9 times 10 to the minus 4 volts. This gives a time of 1.3 seconds. In question 4.5, the coil is now rotated, where to calculate the angular speed to give a maximum reading on the oscilloscope of 5.1 millivolts. Well, we can use EMF is equal to magnetic flux density B, area of the coil A, N for the number of turns, omega, sine omega t, where omega is the angular velocity. The maximum is when this term here is a maximum. The maximum a sine can be is 1. So that is when sine omega t is equal to 1, and we're left with the EMF is equal to B A N omega. We want to find the angular speed omega, which is then EMF over B A N, and the EMF is 5.1 millivolts. The magnetic flux density 0.38 Tesla. The area is 32 millimeters squared. And the number of turns is just 1. This gives an answer of 13 radians per second.